Dear Michelle Brown, dear Daria Galimberti, dear Professor Thomas, dear members of the jury, dear Professor Dao, and dear Professor Hess, ladies and gentlemen. I'm very delighted to welcome you this afternoon to the award ceremony for the Clara Immerwahr Award. In 2011, our Cluster of Excellence Unifying Concepts of Catalysis, UniCat, started to bestow this award. The tradition has been taken over by the cluster UniSysCat, and I'm glad about that. This year, we have, for the first time in the history of the award, not one, but two awardees. I understand the jury was struggling quite a bit to decide for only one candidate when they simply faced two extraordinary candidates and decided for two. TU Berlin considers the promotion of women in science as extremely important. And we're very proud that the Clara Immerwahr Award is another tool to foster this goal. We are therefore very pleased to provide our constructive and financial support to the UniCat Cluster of Excellence, UniSysCat Cluster of Excellence, for this award ceremony. For many years, politics, industry, and universities have criticized that too few women opt to study degrees in the natural sciences, in particular in the natural sciences and in engineering. And TU Berlin is very much aware of this problem. We see a basic need for action at all levels of the academic career path. From the motivation of young women to opt for a degree in science and engineering, or the decision by a young female scientist whether to complete a doctorate, right up to acquiring a postdoctoral lectural qualification. We do not only consider it as highly relevant, since more than 20 years we've also put a lot of effort to reach this goal. TU Berlin has implemented a wide range of innovative programs and measures in order to meet the challenge. And these efforts of the whole university and its members show their results. TU Berlin holds the highest category of the German Research Foundation's research-oriented standards on gender equality. TU Berlin was certified as a family-friendly university. And in the end of 2014, the achievements and efforts of TU Berlin in the field of equal opportunities were distinguished with the Total Equality Award for the third time. Many more awards could be highlighted here to underline our efforts regarding the goal to promote women in science. In 2007, the Clara von Simpson Award was founded, a prize given to female master's students for outstanding final theses in scientific and technical disciplines. At the same time, the award is intended to support upcoming young female scientists in their decision to pursue an academic career. The Clara Immerwahr Award has been created to reward the outstanding research in the field of catalysis of excellent female scientists who have already decided to pursue an academic career. This makes the award an invaluable addition to an extension of existing measures aimed at promoting exceptional young women in science. The award is also signed within our university to foster our institutes, our clusters, and research groups to foster the idea of promoting female scientists, and the UniSysCat cluster is an excellent example of this. I would like to say thank you to the spokesperson of the cluster, to Arne Thomas. I would like to thank also the vice spokespersons, Matthias Dries and Holger Dobek, together with their partners in the catalysis community in Berlin and Potsdam. We have to thank them for making TU Berlin's successful candidature in the very competitive excellence initiative and excellent strategy of the German federal and state governments possible and successful. I would like to also thank the cluster's gender coordinator, Claudia Nasrallah, for her enormous initiative, and I would also like to extend my thanks to the jury for their commitment and hard work. Thanks also to Professor Dao and Professor Hess, the laudators in the afternoon. Thank you very much. I'll pass on to Professor Thomas.
Yes, thank you very much. Thank you very much, Professor Thomsen. So, welcome. Good afternoon, dear Dr. Brown, dear Dr. Galimberti, dear Professor Thomsen, dear Professors Hess and Dao, and dear colleagues. So, welcome. It's really a pleasure. It's a particular pleasure to welcome you all to the 10th award ceremony of the Clara Immerwahr Award, which is bestowed by the Cluster of Excellence Unifying Systems in Catalysis. You are, of course, aware that we started within this cluster a very challenging endeavor, which is nothing less than to change the way we are doing catalysis in the future. So we are all convinced that catalysis is much more than the textbook example of having a catalytic active center and the reactant and the product. But what we learn from nature is that we have to expand our focus. We have to get actually from the single catalytic reaction towards whole catalytic systems, which are actually coupled catalytic networks. And I think we also all agree that to understand and finally actually create such coupled catalytic networks and catalytic systems, we need, of course, first of all, a team of committed researchers. And of course, we need expertise from different fields. And this is actually combining expertise in biology, in chemistry, in material science, in theory, and in methods and method development, of course. I think we were able to merge just such a team of researchers who are actually combining all this expertise, but further support is, of course, always welcome. And yeah, one way of further connect outstanding researchers to our cluster is the Clara Immerwahr Award, because this Clara Immerwahr Award is awarded to outstanding young female researchers. And the motivation is, of course, to establish close collaborations to our cluster and to working groups within the cluster. And I'm very proud to say that over the past years, I think we were very successful in doing this. So really to identify awardees for our awards. You have seen them also in the movie, which are coming from all over the world and which are actually experts in all these research areas I just talked about. And this year, as I said, in the 10th year of the Clara Immerwahr Award, I'm happy to announce that we have actually followed up on this path. So we have again 2 outstanding female researchers. One is coming from the field of theory, the other one from material science and electrochemistry. So please join me in congratulating Dr. Daria Ruth Galimberti and Dr. Michelle Brown. 2 very actual pictures. If you wonder, these were taken actually today, this morning, at the get together with our female students, female PhD students from the UniSysCat club. And I hope actually you had a motivating and stimulating discussion with them. So congratulations. Yeah, if you have paid close attention, you have seen indeed these are 2 awardees for the first time now at our 10th anniversary. And Professor Thomsen was totally correct. The explanation is such simple that we had again, and this is always great to see, we had a lot of really outstanding candidates. So there are a lot of very, very good female researchers, and 2 of them out of this crowd stand out even a bit more. And then it was just not possible for the selection committee to vote for one and against the other, let's say. So, and therefore in the end, it was just decided to say, why not? If we have actually 2 candidates with this quality, then let's give the award to both of them. So my congratulations again. You will not hear anything about their scientific achievements from me now, because we have luckily 2 colleagues, Professor Hess and Professor Dau, who will give a laudation on both of the awardees. So I thank you very much, both of you, for your willingness of doing this. Here you see the program. I will hand over in a minute to Holger Dau to give his laudation for Dr. Michelle Brown. But before I'm doing this, thanks for the financial support to TU Berlin and the German Science Foundation. We had over the years often also their company name who was sponsoring this event. So during Corona times, everyone is actually holding back his money, but can just actually motivate everyone who has connections to industry and friends at industry. Here could be your company logo. And this would really show that you are serious when you say that you are supporting diversity and young female researchers. So hope next year we will find again another company sponsor here. And then last but not least, a big thanks to the selection committee. So Professor Holger Dau, you will see in a second, and Professor Peter Hegemann, Professor Beatrice Roldan, and a special thanks is going to Professor Ulla Wollenberger, who has supported the Clara Immerwahr Award in the selection committee from the beginning. And now after 10 years, she will retire from the selection committee. So thanks to all, and a special thanks to Ulla. Hope she's hearing me. All right. And with this, I thank you all very much for your attention and would hand over to our colleague, Professor Holger Dau. Mikrofon.
Holger, we can't hear you.
Okay. It's a great pleasure for me to present the laudatory speech for Michelle Brown. Michelle Brown is currently at the University of Dublin at the Trinity College, and she's honored for her outstanding achievements in the field of electrode systems for water splitting catalysis. Her work in this area of this field, whatever, can be summarized in two periods. She worked two interrelated periods of topics. So Michelle has been working on electrocatalytic materials for water oxidation, and in a second period of work on 3D printing methods, on seminal work of 3D printing methods for electrode cells and generally for electrochemical energy applications. After studying analytical sciences, which is mostly chemistry, analytical sciences in Dublin, getting a bachelor there, she pursued her PhD with Michael Lyons and Paula Colavita, her two supervisors, and in April 2017, she got awarded her PhD in electrochemistry and material science. And it was a very successful PhD. So with a lot of really important work done in this time of her PhD. And this work was centered on catalyst materials for the oxygen evolution reaction. Two examples, to highlight examples, are shown here. For example, a study in ACS catalysis in 2016. I also highlight here another study which was published in a less flashy journal, more known to specialists. But it's remarkable because it kind of unites or starts with unification of classical electrochemical methods, solid electrochemical methods, with this new type of catalysts which are now studied so frequently. After her PhD, Michelle moved on. After a short period, postdoc period in Dublin, she moved to Belfast, where she broadened her horizon, her expertise in the area of dye and semiconductor photochemistry or photocatalysis. Subsequently, there was in the second period, or a further postdoc period, where Michelle was working in Prague with a well-known group of Professor Martin Pumera, with a Marie Curie Concept Fellowship. And this was the period where she developed the 3D electrode printing methods. During this time, she also received a grant from the Royal Society, got awarded a Royal Society grant, the Electrochemical Innovation Lab in London for 3 months. 3D electrode systems for electrochemical energy calibration, there are multiple facets to this topic, and it's kind of verifies the expertise of Michelle, but she's the first author of a review article in Chemical Reviews, and the chemists know well that this is the most prestigious reviewed journal in chemistry. So the idea is to use 3D printers to print electrode systems, which are sometimes conductive, sometimes non-conductive, and in this specific example, coated with atomic layer deposition methods to get structuring on the micromillimeter scale as well as at the atomic scale. After having pursued this really successful postdoctoral research in Prague, Michelle returned to Ireland. She got a Marie Sklodowska-Curie Individual Fellowship. And this is a fellowship of the European Union, which is extremely competitive and prestigious. So I think it's the most prestigious and competitive fellowship in Europe. And she got it for a project titled Trifunctional Catalysts based on layered 2D materials for water splitting, fuel cells, and supercapacitors. And on this topic, which kind of unites previous work topics of water oxidation and electrode development, 3D electrode development, she's now working in the framework of a group of Valeria Nicolosi. To sum up and to expand a bit on what I said before, so Michelle is honored for her truly outstanding contributions in the development of electrode systems for water splitting catalysis, which she has described in 36 highly cited articles. With highly cited, I mean with an H index of 19, which is for A in comparison to her age. It's really impressive. She's also active in various other directions. For example, she got awards. She's active as an early career advisor in the advisory board of a Chem Electrochem, organizing early career conferences. She's an outreach editor of Applied Materials Today. And in addition to this really productive scientific career, she pursues sporting activities like baking, like most many chemists do, and very soon she will become a mother of her first child. And it's really, I think, an impressive career, and certainly I'm pretty optimistic, but we have selected an excellent Clara Immerwahr Awardee. And as you may know, this award is also meant for the awardee to visit Berlin for collaborative studies. And I'm really looking forward to meet Michelle in Berlin, hopefully very soon, to approach collaborative studies. And I thank you all. I thank Michelle. I congratulate Michelle to all her achievements. And I thank you for your attention.
Thank you very much. Then we will directly switch over to the talk of Dr. Michelle Brown, please.
So obviously I would have a technical difficulty of not unmuting myself. So first of all, just let me thank everyone for joining us today. I especially would like to thank Professor Thomas and Professor Dow for their lovely introductions. And I'm very excited to come over to Berlin to start some collaborative research. I also just want to say, just before I start my talk, it was a wonderful morning meeting all your female PhD students. I think they're a credit to your institution and you should all be very proud of them. So as Professor Dow said, I'm one of the 2 Clara Immerwahr awardees this year from UniSysCat. And I also just want to thank the selection committee for choosing myself as one of the awardees. So my name is Dr. Michelle Brown, and Professor Dow has told you all about me, so there's no need for me to introduce myself. Thank you very much. So I'm just going to go straight ahead in. So first of all, my talk outline today is going to be some motivation and introduction behind electrochemical water splitting, and more specifically, the oxygen evolution reaction, or the OER. Then I'm just going to give a little bit of a talk on 2 research areas that I'm currently doing in Trinity College Dublin in Valeria Nicolosi's lab at the moment. One of the research topics on the electrolyzer devices has been published, and the first one on synthesis of materials for alkaline OER and specifically for post-synthesis processing is currently, some research has been published and then others is still ongoing. So I'm going to talk a little about that today too. So the motivation behind my work, essentially every year, the International Energy Agency will publish the key world energy statistics document. And each year, this document details about some of the energy consumption that we have in the world. So in 2020, the 2018 statistics were published. So in 2018, the world energy consumption was approximately 9.9 GTO. So some people might be like, 9.9 GTO, what does that even mean? So to break it down a bit, this is approximately the energy released by burning 700 million barrels of crude oil, which is quite a lot of fossil fuels. So if we keep on this current path, we're going to have our current fossil fuel reserve all depleted by the year 2112. So what are we going to do about it? So before I go in to tell you what I'm doing about it, I also just want to say that the burning of these fossil fuels also will cause nasty greenhouse gases to be emitted that can have detrimental effects on our environment. So now is the time that we need to essentially research into alternative energy generation routes and concepts. So my work focuses on the hydrogen economy concept. So what this is, it's a concept that was coined by a scientist named John Bockris in the 1960s, 1970s. And essentially what it describes is the production, storage, distribution, and utilization of hydrogen as an energy carrier to make electricity. So in a simple hydrogen economy concept, which you can see on the screen, you will have power being generated by wind or solar renewable energies. This will then power an electrolyzer. So the electrolyzer is where the hydrogen is produced. The hydrogen can be stored for later use, or it can be used directly in a fuel cell that is attached onto, say, a building or in a car, and it can produce electricity. So in this overall concept, I work on the electrolyzer devices. So essentially, in an electrolyzer device, you will simply have the splitting of water into hydrogen and oxygen. So if you look at your left-hand side of your screen, you can see a schematic. And on the cathode, you will have the hydrogen evolution reaction, or the HER. So this is where the hydrogen is produced, and this is our main goal. We want to try and capture this hydrogen to be used as an energy carrier to make electricity for the masses. However, the opposite reaction, the oxygen evolution reaction on the anode, is the bottleneck reaction of overall water electrolysis. So this is the reaction that I work on, because if we make this more efficient, essentially we can make more hydrogen. So currently, if you see on the screen here, you can see an equation. So the equation underneath the oxygen evolution reaction and hydrogen evolution reaction are the 2 equations for these 2 reactions in acidic and alkaline media. So for an acidic media, the water electrolyzer devices are also called proton exchange membrane electrolyzers. And then in alkaline media, they are called alkaline exchange membrane electrolyzer devices. So the overall, just getting my pointer out here, the overall cell potential of water electrolysis will depend on a few different factors. So one of the factors is the thermodynamic potential of water electrolysis, which is 1.23 volts versus RHE, or the reversible hydrogen electrode, plus essentially the excess energy or overpotential related to the hydrogen evolution reaction, plus the excess energy or overpotential associated with the OER or the anodic reaction, then plus any ohmic losses that we can have in our cells. So what I particularly work on is the state-of-the-art materials for these devices. So for PEMs, or proton exchange membrane devices, the state-of-the-art materials are the very expensive iridium and ruthenium dioxide. And this is because they produce oxygen at the lowest known overpotentials at various current densities. And then again, for alkaline media, the best electrodes or best materials will be nickel-based. However, both of these state-of-the-art materials have their cons as well, or their disadvantages. So for proton exchange membrane state-of-the-art materials, these materials are very expensive, and they're also quite unstable at operating conditions. And then for the alkaline exchange membrane state-of-the-art materials, they have a lot of health adversary effects. So nickel complexes and nickel-based materials are actually carcinogenic. And then also, when you compare the alkaline state-of-the-art materials to the proton exchange membrane materials, they are significantly worse to produce oxygen when compared to the acidic-based ones. So essentially what we want to do, and what my research is all based upon, is to develop efficient, stable, and cheap electrocatalysis catalysts for the OER in both of these electrolyzers, because at the end of the day, we can't predict what materials we make. So we have to work on both. So for my first part of my talk today, I'm going to talk a little bit about one of the fields of research we're currently conducting in Valeria's group on nickel-iron LDHs. So essentially, I'm going to try and show you how we utilize post-synthesis processing to enhance the OER activity of a catalyst. And the reason that we chose the nickel-iron LDHs is because they're extensively investigated in the literature for OER catalysis in alkaline media. So to make our materials, so to make these nickel-iron LDHs, Sonia, which you can see her in the picture above here, she is the synthetic chemist who made these materials. And essentially what Sonia did was she used a low temperature co-precipitation synthesis method. So essentially you will have your metal precursors with urea. You will stir them for 24 hours at room temperature. You will then add in TEA. So essentially what you will make here is two different intermediate catalysts. So you will make a nickel TEA based catalyst, and then you will also have some iron oxy hydroxide material too, which is the brown color, which you can see here. So then this solution is then added into a round bottom flask and is refluxed for 48 hours. And essentially what we get at the end, or what Sonia gets at the end, is very nice nickel iron LDHs. So just to characterize them a bit. So if we first of all look at figure A, we can see that these platelets have a lovely hexagonal shape. And we can also see this from the TEM micrograph as well. So also what's very important, I think, is if we want to show what post-synthesis processing does to our materials, we have to have a very crystalline and also a very pure material to start with. So from the SAED pattern and the XRD, Sonia was able to show that there is a hexagonal pattern symmetry as well as shape, and the material is solely composed of nickel iron LDHs, which is great. So then just to show this visually, I think everyone loves the SEM EDX mapping. So in figures E, F, G, and H, essentially, we just again see the SEM micrograph, and then the EDX maps of the nickel K alpha, and then the O, and then the FeK alpha, showing that we have these elements here, and they're solely comprised of nickel and iron. So further on, we wanted to look at then the OER activity of these materials, because there was no point of doing more studies if our material wasn't OER active. So first of all, the material was sprayed onto nickel foam, which is a well-known support for OER alkaline medias. So if we then look at the LSV curves here for the OER activity, the red curve is just the bare nickel foam. And then once the nickel iron LDHs are deposited, we can see that we get an increase in OER activity. So everyone was very happy. So what about some post-synthesis processing of these materials to try and make them more active? So currently in literature, when I look in literature anyway, I see a lot of groups using chemical processing methods. So they will try and dope their materials, or they will add in some additives such as carbon nanotubes to make the activity better. But what if you use mechanical type post-synthesis processing? So Daria, one of the PhD students in Valeria's lab, who actually passed his Viva a few weeks ago, so he's now Dr. Daria, carried out this work that I'm going to talk about now. So essentially, Daria used tip sonication methods to essentially fragmentate the lovely hexagonal shapes that you have into these shapes that you see here. So Daria was then able to use the SEM images and a software called ImageJ to essentially determine the sizes of these materials. So L, when you see L anywhere in this presentation from now on, that is the longest possible measurement across a flake, essentially. So when we look at the size distribution of the as prepared nickel iron LDHs to the tip sonicated ones, we can see that there is a massive decrease in the size of the tip sonicated materials. And now we also wanted then to look at the OER activity of these materials. So again, the same way as we prepared the as prepared material on the nickel foams, this was done exactly for the tip sonicated materials too. So first of all, in the black LSV, this is the as prepared materials in alkaline media. And then once we run the LSV of the tip sonicated nickel iron LDHs, we can see that there's a cathodic shift in the OER activity, which tells us that we are getting better OER activity. So this is super, but is there any way possible that we can perhaps enhance on this? So what Daria did was use controlled stepwise centrifugation to size select the various nickel iron LDHs from the tip sonicated solution. So essentially, Daria used a centrifuge, and then by changing the various centrifuge speeds, he was able to isolate different sizes of his nickel iron. So if anyone wants to look further into this, you should look at this paper down here by Claudia Becks and Jonathan Coleman. It will tell you all you need to know essentially about using liquids cascade centrifugation for size selecting your different materials. So then just back to Daria's work. Essentially, Daria then used scanning electron microscopy and again the ImageJ software to look at the different sizes of the flakes with increasing centrifugation speeds. So what was able to be concluded here is that at increasing speeds, you get decreasing lengths of your flakes. So again, these materials were deposited onto our nickel foams. And the trend that was able to be revealed essentially by looking at our LSVs here is that when you have the higher rotation speeds for your centrifugation, you get better OER activity, which tells us that the smaller flakes are more active for the OER. So this trend is actually seen for this trend and is followed by the 4000 RPM, which is the middle OER material for the three different centrifuged materials. And then the worst one, or it's still actually a pretty good material, is at the 500 RPMs. And then if you just want to compare them to the as prepared materials, the LSV for the as prepared nickel iron is seen here in the red here. So by using these various mechanical post-synthetic processes, Daria was able to significantly enhance his OER activity of his nickel iron LDHs. So just to summarize then, if we plot over potential at a whatever current density you like, so we pick 10 milliamps per squared centimeter, which is the benchmark material used in the literature, you can then plot the size of your flake, which is the longest possible measurement across the flake, and plot your activity. So what we essentially see is that your as prepared material has the worst OER activity in this study. Then once tip sonification is used, you get better OER activity. But then once you size select your materials, you can see this enhancement in the OER once you use higher rotation speeds. So as we are all chemists and physicists, we wanted to try and understand why this is happening. We just didn't want to know what's happening. So we wanted to try and rule out a few chemical changes that could have been happening. So first of all, we looked at the crystallinity of the materials before and after tip sonication, then also the chemical state before and after tip sonication, and then also the thickness of the flakes. So first of all, XRD, or X-ray diffraction, was used to see if there's any changes in crystallinity after tip sonification. And by looking at the XRD patterns, essentially the reflection peaks are the same. Positions have not changed. So we could rule out any changes in crystallinity for any increase in OER activity of our materials. Second, we also then wanted to look at any chemical changes or any introduction of any defect materials. So to do this, we looked at X-ray photoelectron spectroscopy, and XPS is a very vital technique in electrocatalysis because it tells us a lot of information about the surface of our catalysts. So by comparing the as prepared nickel iron LDHs to the tip nickel iron LDHs, I need to learn that word better. We were able to conclude that from the survey that there was no defects introduced, and also there is no other elements at all introduced. So say from the tip sonification, sometimes you can get introduction of titanium, and this wasn't happening in this instance. But then to further look at the actual chemical state of the nickel, we were able to fit the Ni2P peak with an indicative XPS pattern, essentially found in literature for the nickel iron LDHs. And what we can conclude from the fits is that there was nickel 2-3 in both. And also these peaks happened at the same binding energies, and also before and after tip sonification, also in similar concentrations. So we also concluded that there was no change in chemical state that could affect the OER of these materials. Then last, what about the thickness of our flakes? Because if the thickness of our flakes severely decrease, we could be getting exfoliation and not just fragmentation, which can also increase the density of our sites. So if we look at the results from the atomic force microscopy, first of all, we can see that the as prepared nickel iron had an average height of their flakes of about 14 nanometers. And then for the tip and centrifuge materials, there was no actual trends that we could correlate to the OER activity. So again, we ruled out thickness of the flakes. So essentially, what is happening is that it's really simple. The fragmentation is causing an increase in edge density sites, in site densities, which improves the OER, which also tells us that the OER is preferential to edge sites and not the basal plane sites. So the reason that I wanted to show this research in particular is because anyone in OER catalyst research can use these methods to try and increase their OER activities, as well as their chemical means that are currently used. So for the second part of my talk, which I think I'm okay for, this is a paper that was published two-ish weeks ago, I think. And this paper shows about the importance, I think, of collaboration in science. So this paper and this research was conducted in 3 different institutions in 3 different countries. So we all had different expertise coming together. And the title of this is Electrolyzer Devices versus Rotating Disc Electrodes for Proton Exchange Membrane OER Materials Evaluation. So I'm just going to talk a little bit about my motivation behind this work. So when I started as a PhD student, I just, like all PhD students, we do as our postdocs and our supervisors tell us. But I think then as you grow in your career, you start to question what you're doing. And the platform that I was using at the time was a rotating ring disc electrode, otherwise known as a 3-electrode cell, for evaluating my materials. And I started to question, is this the right platform to evaluate materials for electrolyzer devices? Because they're totally different. So say for other electrochemical technologies such as batteries, the development of the catalysts was predominantly done in academia. And we all seen this being honored by the Nobel Prize in 2019. So if it can be done for batteries, why has there's been no progress in OER materials in the last 60 years? So I'm just going to give a brief description about the work that I did here, and hopefully you will all agree with me, but I'm going to put in a lot also of my own opinions and stuff into this too. So essentially, when you look at the conventional 3-electrode cell that's used in academic labs, and then you compare it to a proton exchange membrane device, which you can see here, it's totally different. The operational parameters could not be more different. So for the electrolyte in the 3-electrode cell, we use liquid acidic acid, so normally H2SO4, but then in the device, it's a membrane. And then the feeds that you put into it, the liquid feed, is water. The catalyst loadings differ significantly. The working electrodes that we use in the 3-electrode cell is made of glassy carbon. So glassy carbon itself actually corrodes and pits under acidic conditions itself. So if you continuously use this material to evaluate your catalysts, you will even get changes in the active surface areas because of the pitting, but most people won't realize. Then for the actual proton exchange membrane devices, the working electrode material is the Nafion membrane, and I will show you what I mean by this is the working electrodes on the next 2 slides. Then the different geometric sizes also completely differ, and even the temperature that these 2 devices are operated at significantly different. So for the 3-electrode cell, it's room temperature, and then for the proton exchange membrane device, it's between about 50 to 80 degrees. And this will significantly change the kinetics of your materials. So the question that I propose essentially for this work is the current evaluation technique for OER catalysts representative of the catalyst activity and stability in electrolyzer devices, which is the main goal, which is what is put on large scale to make electricity in the real world. So to do this work, essentially, I made 5 different catalysts through the Adams fusion synthesis method. So this is a very simple method. You just get metal salts with sodium nitrate and water into a muffle furnace at 500 degrees for 30 minutes. You clean and you centrifuge your materials, and then you have your catalysts. So I altered the metal salts 5 different times to make 5 different transition metal oxides. And these are the 5 transition metal oxides that I use for this study. So for most of the materials, we had an exact phase. But for the manganese metal salts, we had a mixed phase, but I can't stress enough, because this is not trying to find the best OER catalyst, it's trying to evaluate 2 different platforms. We didn't need an exact phase of our catalysts. We just needed the same material to be used in both different platforms. So from our catalyst inks, first of all, we made our catalyst electrode preparations for the RDE, or the 3-electrode cell, through drop casting with for loadings and active areas, which are very common in literature. So essentially, you drop cast, you let it dry, and then you will push your electrode onto your rotating ring disc, and you will perform your OER catalyst measurements. But for an electrolyzer device, it's completely different how you make your catalysts electrodes. So essentially, an electrolyzer device, you will use a Teflon sheet first, and a catalyst mask. You will then spray your catalyst onto your Teflon sheet. And this is essentially one side of your catalyst coated membrane material. So then you do this for one side. So you do this for your anodic side, and also the same for your cathodic side, which is your HEOR. And then you will get your Nafion membrane, and you will sandwich your two Nafion sheets for your catalyst between the Nafion membrane and hot press. And then eventually what you get is a catalyst coated membrane, which you can see here. And the catalyst loadings are significantly different and the active areas compared to our rotating ring disc electrodes. So then after this, the catalyst coated membranes will be inserted to an electrolyzer device. So this is a schematic of the electrolyzer device that we use for this study. So to directly compare the OER, so the anodic side of our electrolyzer device to a rotating ring disc electrode, we used a reference electrode. So we were purposely just measuring the OER in the electrolyzer device. So for the results that I show you here, for your activity at 10 milliamps in the rotating ring or disc electrode setup, essentially what we get is we can see that the ruthenium dioxide, which is also known as the state of the art, performs pretty well. However, for the first row transition metal oxides, they essentially all corrode once they get into the acids. And then for the same materials in an electrolyzer device, they all reach 10 milliamps per squared centimeter, either before or at a potential of 2 volts versus RHE. So now if we look at the stability, so if your material corrodes in LSVs, they're not going to be able to be measured for any stability tests. And then also for the ruthenium dioxide, which is state of the art, this essentially also gets corroded, or it might be passivated at around 40 seconds. So if anybody was doing these studies on these materials in a research lab, you would totally omit these studies from any further investigation. But in the electrolyzer device for the stability tests, these materials are all quite stable up to a period of 7 hours, except for the nickel oxide. But that's understandable because you will always have some materials that perform worse than others. So based on these results, I would say that the rotating disc electrode does not show us the correct results that you will get in an electrolyzer device. So if you look at the different parameters that I was talking about, so catalyst prep, active area, and electrolyte, we can't change these parameters in the rotating ring disc electrode to try and make it a better platform or more representative of catalysts in electrolyzer devices, but we can change the catalyst loading. So we just did a quick study where essentially we used the ruthenium dioxide at a catalyst loading that you would in the device on a rotating disc electrode. And if you look here, you can see in the dashed line, this is the ruthenium dioxide at 3 mgs per centimeter squared in the rotating ring disc, but it's still nowhere near the activity of this material in an electrolyzer device. And same goes for the stability. In the dashed line, it's the same catalyst loading as the electrolyzer device, but it still doesn't show anywhere near the same activity. So there definitely is a problem, I think, in my opinion, of the rotating disc electrode being the correct platform for OER catalysis evaluation for electrolyzer devices. And so we're not actually the only group, I don't think, that's realized this. There's been a few papers in the last few weeks on this work too. And then also Professor Shannon Botcher in America has also showed similar results for the OER catalysis evaluation for the rotating ring disc electrode in alkaline media too. So this is just my last slide. So to try and overcome this, I used some of my previous knowledge on 3D printing to try and make 3D printed electrolyzers to evaluate our OER catalysts under electrolyzer conditions in our labs. So to do this, we essentially use 2 different cheap 3D printing techniques called fused deposition modeling and stereolithography. So if you can see, these are B, C, D, and E are the electrolyzers that we 3D printed. And A is the standard practical electrolyzer cell that we used for the previous studies on the last slide. So to compare our 3D printed electrolyzers to our peak cell, we used a commercial ruthenium dioxide and platinum CCM or catalyst coated membrane materials. So if we look at the activity of the same CCM in all the different devices, we can see the activity is pretty good for all of them. So essentially you can use any one of these 3D printed electrolyzers to successfully evaluate the activity of your material. However, when you're looking at stability, we run into a few problems with the two stereolithography 3D printed materials, which is D and E, as these are made from high temperature and low temperature resins. So essentially what we think is happening, that we get a decrease in the activity over time for the same CCM in these two electrolyzer devices, is due to the fact that the actual electrolyzer resins are degrading with time, because in an actual electrolyzer device, you use 50 to 80 degrees. So essentially you're getting higher resistances because your material is wearing away, and it's not, the CCM isn't being bounced with your electrolyzer device. So you're losing resistance in your cell. So the I/or part of the equation that I showed at the start. So finally, just a quick cost comparison. If we use the 3D printed electrolyzers of B and C for our catalyst evaluations, anyone can essentially make these in their lab. Fused deposition modeling is child's play. And it costs approximately less than £3 to make these electrolyzer devices, which is quite cheap. So that's it for my presentation today. Just a few acknowledgements. So first of all, I would like to thank Valeria Licolosi for letting me be a part of her amazing group in Trinity College Dublin, and also especially to Daria and Sonia for the nickel iron LDH work. And then for the electrolyzer work, I really want to thank Professor Dan Brett in UCL, who allowed me to come over there as a researcher and learn a lot about electrolyzer devices. And just to everyone who has helped me in my career so far. And I really just want to thank all my friends and all my family, because I think behind every success is a village of people. And these are all the people that have helped me, especially my dog. And as always, remember where you came from. So this is a picture of me when I was smaller, and this is a sonogram of my unborn baby at the moment. So always remember while you're doing your research, essentially. So thank you all for your attention, and I hope you enjoyed my talk.
All right, thank you very much. I think this is always the most annoying on this situation, that you give an excellent talk and then you hear nothing, silence. At least, so applause from my side, and I'm pretty sure that everyone watching this is totally excited in the moment. And also thanks a lot for the important last works, actually. So remember why you are doing your science. So normally I would come on stage now and hand over the certificate, but this we can at least send via email, of course. So this is possible. I think actually the people watching will see the certificate now. What we can't do, of course, is send you via emails also some flowers, which we always like to hand over. At least I have them here. And now we will send them. You see how fast we are. There we go. They are already there. You see, that's the cluster of excellence UniSysCat in seconds. We have not practiced this, I have to say. No, thank you very much for this exciting talk. Also, thanks again to Holger Dau for the laudation. And with this, I would like to hand over to Professor Franziska Hess, who will give the laudation for our second awardee, Dr. Daria Galimberti, as far as I know. But before we start, we will actually see a short video again. And then after the video, I think Franziska can start directly.
Dear President Professor Thomsen, dear Professor Arne Thomas, dear Clara Immerwahr Awardees, Professor Dr. Daria Galimberti and Dr. Michelle Brown, dear colleagues, dear ladies and gentlemen, we have come together today to honor two outstanding young female researchers in catalysis. It fills me with particular joy to be given the honor to give the Laudation for Daria Galimberti because we share a common interest in the development of new computational methods, and I believe that we can all learn a lot from her. Daria Galimberti, born in 1987 in Milano, got her bachelor's and master's degrees in materials engineering at Politecnico di Milano in Italy in 2010 and 2012. She developed a particular interest in modeling spectroscopic data in semicrystalline polymers and other molecular materials very early in her career, and used insight from spectroscopic data to develop a deeper understanding of charge and charge fluxes in the interaction between molecules. Her talent and commitment, together with the good results she obtained in her first experiences of scientific research, allowed Daria to win a scholarship to attend the PhD program in materials engineering at Politecnico di Milano. She completed her PhD thesis in Chiara Castiglioni's group, for which she was given the highest honors in 2016, on first principles modeling for the prediction of the structure and the spectroscopic response of molecular materials. She then moved on to France to join the group of Marie-Pierre Guégeot at Université d'Evry-Val-d'Essonne for 3 years as a postdoc, where she worked on advancing the prediction and interpretation of vibrational spectra in liquids. She then joined the group of Joachim Sauer at Humboldt University Berlin as a Humboldt Fellow, deepening her research on computing accurate free energies of reaction and activation from molecular dynamics simulation. Last year, she actually accepted a tenure-track assistant professor position funded by the Christine Mormon Fellowship Program at the Institute for Molecules and Materials at Radboud University in Nijmegen in the Netherlands. Her special area of expertise is the development and application of molecular dynamics methods for predicting and analyzing vibrational spectra for complex condensed phase systems, notably systems with interfaces, which is particularly difficult and challenging. Her work has been presented at numerous international conferences and published in renowned scientific journals. She's well connected throughout the work through her fruitful collaborations with experimental partners in Germany, the Netherlands, and in the USA. In her work, she thinks out of the box and does not shy away from following unusual approaches to reach her special goals. When she first proposed, for instance, to combine atomic polar tensors in combination with graph theoretical tools for assigning spectroscopic signals to structural elements in molecules, as you can see on the slide here, her proposition was met with great disbelief, even by her close colleagues. However, she knew that her idea would work, and her results speak for themselves. During her postdoc years in Paris and Berlin, she also contributed to understanding the interfaces of water with air and solid surfaces, to understand the role of these interfaces in catalytic reactions. In this line of work, she used molecular dynamics to assign spectroscopic signatures to structural features of these interfaces to assist in the interpretation of spectra collected during peptide binding reactions. She then applied this concept to the solid-liquid interfaces of silicon dioxide, zeolites, and cobalt oxide with water, all of which are materials highly relevant for catalytic and electrocatalytic applications. In recent years, she has started a new area of research where she's developing methods to compute vibrational partition functions using normal modes of vibration extracted from molecular dynamic simulations. This opens a very efficient way to ab initio free energies for molecular surface reactions, which are key parameters for the prediction of activation energies, reaction rates, and equilibrium constants in heterogeneous and electrocatalysis. To quote her PhD advisor, Chiara Castiglioni, Daria Galimberti is actually one of the most brilliant students who attended my lectures. And even with my own little understanding of the spectroscopy of liquids and solid-liquid interfaces, I can tell that her research is extremely challenging and ambitious. She has recently started her own group as an assistant professor at Nijmegen in the Netherlands, and given her track record so far, I am certain that we can expect great things from her. Let us all join in congratulating Daria. We are looking forward to your talk, from vibrational spectroscopy to heterogeneous catalysis, a DFT-MD route. Thank you.
Sorry. First of all, I would like to thank you, Franziska, for the beautiful introduction. It has been really, really nice. And then I want to really thank the UniCat for this award. It's really, really a big honor, and I'm really happy to be here to give this talk. And I hope that this will be a start of a long-standing collaborations. And what I would like to talk with you today is what vibrational spectroscopy and DFT and simulation can do for heterogeneous catalysis. So these are a few examples of what is heterogeneous catalysis for our society. So heterogeneous catalysis involved, for example, in water splitting, in the production of synthetic rubbers, in the CO2 reduction, in the activity of design. And there are other thousands of examples. And if you want to really be able, and I know that this is a things that we always say, maybe a little rhetoric, but it's really true. If you want to really be able to design new materials with the desired properties, the materials that we really need, what we need to do is to understand first what is happening and why. And the second is why. Because it's the only way in which we can understand what is working and what is not working. And so to be able to correct what we don't want in these materials. And what I hope to demonstrate with this talk is that with the combination of DFT simulation and vibrational spectroscopy, we can not only characterize the materials at the molecular level and so understand what is happening at this level, but also understand why it's happening. But first things first. So Franziska has already shown some example of my previous work on this, but I would like also to show you two fast examples on what we can do with DFT and simulation and vibrational spectroscopy to characterize interesting interfaces. And these two, I want to thank all the people that have been involved in these two works that I'm showing. You can see here with the papers, the names. They are really nice to work with you all together. And the first example that I want to show you is that the silica water interfaces. So silica is one of the most abundant material on the Earth. Water, okay, I suppose that I don't have to say what is a water as solvent for us. And so you can understand how many interesting reactions can happen at these interfaces. And depending a little on the history of the silica and the experimental condition, the silicon can show different degrees of hydroxylation. And for example, you can see that this surface is evolving like using a vibrational spectroscopy. This is the example of the SFT spectrum, so the some frequency generation spectrum with silica water interface at 2 degrees of hydroxylation. However, the point is that if you go with the experiment alone, you have so many factors that interplace together to generate your final spectrum that it's not so easy to understand what is really happening at the molecular level. And in this simulation can give a lot of help, because we can really go and see the molecules, how they are organized, what they are doing. And for example, for the silica interface, what we can see with simulation is that while macroscopically they are both hydrophilic surface, strongly hydrophilic surface, there is no doubt for this. But if you look at what is really happening at the microscopic level, you will see that a change in the degrees of hydroxylation, you see the emergence of these some small hydrophobic patches, this Synanon bridge, that in turn will make a change on the structure of water in contact with the silica surface. And since both the surface and this water layer is changing structure, you change the chemical properties of these interfacial layers. And so changing the energetics of the reaction that happened there. And with simulation, we cannot only looking at it and say, okay, if you are in this condition, you will have this structure. But we can also find marker bands of these different conditions that then we can look at in experiments. And for example, looking how we see our structure is evolved with an in situ experiment. This is for the first example. The second example that I want to show you is the cobalt oxide water interfaces. So cobalt oxide have been proposed as a possible interesting material for water splitting, and in particular for the oxygen evolution reactions. And in particular, this cobalt phase of the cobalt oxide, the 110 surface, if you look at it experimentally, you will see that it's a charged surface. Depending a little of the cut, since it's a double layer materials, you can have a positive surface or a negative surface, but it's for sure a charged one. And when you put this surface in contact with water, this will be rearranged, they will reconstruct, and simulation can tell us how. But most more interesting is that if you look at this surface and say it's charged, what you would expect is the, okay, water will rearrange following the field generated by the surface. But instead, what is something curious can happen is that, and simulation can tell you, is that sometimes, especially when you have this positive, when the positive surface is exposed, what can happen is that you have also a local rearrangement of the water, because this surface can also is also a really good hydrophilic surface. So water is really happy to make hydrogen bond with it, and it's so happy that the water molecules that following the film should point the oxygen to the surface and the hydrogen towards the bulk of water, instead of be a good soldier and follow this field, decide to flip up and do a hydrogen bond, generating an organization of the first water layers that is against what you would expect by electrostatic. And obviously, this will change how the oxygen evolution reaction will proceed and the energetics involved. And also in this case, what simulation can provide you is not only a way to look at what is happening, but also marker bands of this phenomenon. So you can look at them in your experiment and see, okay, if I change my experimental condition, what I have one situation or the other one. However, these are a few examples. I can go on possibly for another 2 weeks with example. Also, there are many works of people working on this in the literature, but in this talk, I don't want to focus on what is happening on the characterization of surface with vibrational spectroscopy and DFT simulation, but I want to demonstrate to you that the combination of these two can give you also information on why it's happening. And to say why something is happening at this level means that you know the energetics that are involved in the process, in particular that you have information about the free energies in this chemical reaction. And why I say that you want free energies, why we are not happy with our 0 Kelvin electronic calculation. And to show you why, I would use this example, then I will bring with me for the full length of this presentation. And these are the Chabazite zeolite. So zeolite are nice, wonderful material for the catalysis because they have a huge surface area compared to the volumes. And in particular, this chabazite and this family of zeolite is used in the methylation of alkanes in the petrol industry. And if we want to think to get better catalyzer, and I think that no one will, the commenter will argue that we need better catalyzer and greener catalyzer for in this field. And if we want to do it, we need to understand which are the energetics involved. And so we need to look at these reactions. And the first step of these reactions is the absorption of the alkanes at the active site, because only in this case the reaction can start. And if you go for your 0 Kelvin calculation, you calculate in practice the enthalpy of the process, and you will say, oh, perfect. My enthalpies are always negative. So my alkanes are always stably absorbed to the surface. I don't have to care of this step. My catalyzer is okay like this. However, then you go in the lab, try to make it work. And what you will discover is that, no, that it's not true. That your methane molecule is not absorbed on the active side because you have a positive free energy. The ethane, it's only weakly stored. So what is wrong? What is wrong is that we need to understand what is happening. We need to take account also these other terms of the free energy and entropic terms. There's as opposite side compared to the enthalpy. These two compensate each other. And so in the end, what you get is that the methane is not absorbed. And so you can see that if we want really to understand what happens, and I make the example of the absorption, but it's true for the full chemical reaction, all the steps, we need to understand not only know with good accuracy this term, but also this one. And so this is our target, what I want to talk with you about, how we can get really accurate energies. And when I say accurate energies, for me, it means that we are below 1 kcal/mole or 4.2 kJ per mole compared to the experimental measured values for any elementary step of our reaction. This is the target of this talk. And to reach this target, we know that this kind of accuracy can be reached in general only if we use quantum chemistry calculation, at least DFT. And the problem is that we also know that the standard method to compute free energies is to use molecular dynamic simulation or Monte Carlo simulation. But this simulation required either long simulation for the molecular dynamic simulation, so from 100 picosecond to 100 nanosecond, or to use million of energy calculations in the case of the Monte Carlo simulation. And this is due to the fact that the entropic term is not only dependent on the contribution, is not taking contribution only from the position near the minimum of the potential on the surface, but it's really feeling also all the other points of the potential energy surface. You really need to have a good description of also this far point from the minimum. And so you can imagine that these two things together, high cost quantum chemical calculation and a million of energy calculation, it's not something that make you happy and you want to do. Because we technically now we have the ability to do this. But if you take 1 year to study a single system, you can see that it's not so a useful method. So how we can overcome all of this? And how we do? Maybe we can go back to what we know by statistical mechanics and say, okay, my total free energy, that is the sum of these two terms, can be separated in different components. And we particularly can separate the rotational contribution, the translational contribution, and the vibrational contribution. And we know that for these two contributions, the rigid body approximation is okay, it's working. So what remains is to compute instead the vibrational contribution. But we also know that if we take the harmonic oscillator approximation, we have a simple analytical solution that is this one. So if we know how to compute the harmonic frequency, we have this. So we are happy, we have solved all our problems. Since, as I told you, compute the harmonic frequency is not a problem. Most of the quantum chemistry code now can easily do it. But if you try to make this calculation, and we come back to our example, this is what happens. So if you look at the enthalpy term here, and these black dots are the experimental values, you can see that, yes, the harmonic approximation worked quite well. We are near the chemical accuracy. We are not so far from our experiment, so we are happy. But if we look at the entropic term, we are off. And we are off by 10 kilojoule per mole, 1050. That it's a lot. And you would say, yes, but in any case, you have the correct trend, so maybe we can be happy with this. And the answer is no, we cannot be happy only by the trend, because since the free energies is the sum of this by this, if we are off with the entropy of so a huge amount, what is in the end happening is that, for example, that your propane, that experimentally is known to be stably absorbed to the surface of 10 kilojoule per mole, in your harmonic approximation, in the end, is not it has a positive free energy values, so it's not absorbed to the surface. And where is the problem with this approximation? The problem is that, as I told you, the entropy terms depends on the full potential energy surface. And so it depends also on the portion of the potential energy surface that is not harmonic. And see, if we really want to have a good description of these entropic terms, we need also this anharmonic contribution to be taken into account. So how to do this? And what has been proposed in the past say, but maybe this equation that I shown you here, this one, is can still be used. But instead of plug in the harmonic values for my modes, I use the anharmonic frequency. And I can tell you this worked quite well, but we have solved a problem and we open a bigger one. Because if you ever try in your life to compute an harmonic frequency, you know that compute an harmonic frequency with the static calculation, as you do for the harmonic ones, is not only expensive, but it's really, really not trivial. And so we are coming back with our initial problem. So we have a method to compute these free energies in a quite accurate way, but it's too expensive that we want really to go for it. And so, can we find a way to escape all of this? And my answer is yes. And to show you how, we can come back to the molecular dynamics simulation. And why my title? Because I told you that to compute free energy directly by molecular dynamics simulation, it means that you need really long simulation, 100 picosecond to 1 nanosecond. However, there are other properties that can be computed by molecular dynamics simulation in a much shorter time scale. In particular, an interesting one that is the vibrational spectra. Vibrational spectra can converge in a time scale that is between 10 to 20 picoseconds. And as you suggested in the vibrational spectra, obviously have the information that we want, that are the anharmonic frequency. In particular, this information can be stored in the vibrational density of state that can be really easily calculated by a molecular dynamics simulation. And so we have a way to find this anharmonic frequency with a short simulation. Where is the trick? Where is the problem? Because there is always a tricky problem in this. The problem is this, that the information is inside this vibrational density of state, that is really easy to compute. However, it's together with other information and other quantities that we don't want. And we have to, in particular, for example, we have the contribution of combination bands inside it. And we need a way to extract what we want to the total Simian. And in since 2014, here in this paper, 2000, also another paper in 2017, I proposed, San et al. And Zhang et al., I propose a method to try to do it that is based on the idea that, okay, what we can do is take our total simulation and we can project it on the harmonic normal mode that we know well how to compute. And then we can, since we know that a normal mode should have a Lorentzian shape, we can filter the signal and extract the harmonic frequency, throwing away whatever we don't want. And this work, they have tested on different systems, and in their case was working quite well. But there is a small problem that even if you look at in this equation, this L matrix, that is the matrix that describes the normal modes, is not depending on time. So it's a fixed quantity. And so we have an underlying assumption that the normal modes are not evolving during our molecular dynamics simulations. That is true in the system that they were studying. But if you think to what we want to do, that is this kind of system in which you have a framework that is vibrating with large amplitude motion. Then you have a molecule that, for example, the C286, the ethane, that have this CH3 that can rotate with large amplitude motion relative to each other. Then the molecule during your simulation can be attached, but can detach, then attach again, can turn around, can rotate. And so you can see that in our case, the assumption that this L matrix is constant time is a bad approximation, cannot be true. And you will say, okay, but what's the problem? I can recompute my L matrix for each time step of my simulation. And the answer is no, we cannot take this path for two reasons. The first one is that it's too computationally expensive. So we come back to our computational cost. But also in the case you say, oh, okay, I want to pay my price, I want to do it. It's not even so trivial because the L matrix is still well defined if you are in the minimum or around the minimum position of your potential energy phase. But when you are outside the minimum, and we are doing this molecular dynamic simulation because we want to describe also this point that are far from the minimum potential energy phase in a way to include this anharmonic contribution, the L matrix is not so well defined. It's why the calculation, direct calculation with static calculation of the harmonic frequency is so complex and computationally expensive. So we are stuck with this. And I would say, yes, we cannot recompute the L matrix at each time step. But what I want to show you with this presentation is that we don't even need it. But because what we have thought, let's start the project and say, yes, maybe we cannot compute it, but why not try to describe the evolution of the L matrix as instead the weight average of the L matrix of a reduced number of reference structures. And when I say reduce, it means between 2, 5, maximum 10. And the weight that we put in this expression is the probability that we are oscillating around the mean. Because it's true that the system evolving will explore the potential energy surface and will go also outside the minimum. But it will try to vibrate around this minimum position. So maybe we can do this. And also to include the large amplitude motion, what we can do is say, okay, instead of try to use the big system altogether, we can divide the system in small fragments and take also into account the relative motion of each fragment compared to the other ones. For example, one CH3 compared to the other one. And what I want to show you is that this way, of this approximate way to build this L matrix is working quite well. And this is why. It is how. In this plot, we are coming back. So dots are still our experimental values. This is the harmonic approximation. And this red line is the real harmonic frequency by static calculation. And this green line instead, it's our vibrational density of state that has been projected on this L matrix built like this. And as you can see, with this simple projection, we are really reproducing the experimental data. We have increased a lot the quality of our prediction on the entropy, and so we have the correct free energy. And I want to underline that for compute this line, we only use 2 molecular dynamic simulation of 20 picosecond each. So, and here, most important, you can see now that while the propane with thermal approximation was predicted to be positive in free energy, so for absorption, now we have the correct free energy of absorption that is negative, and not far from the experimental value. And before I say to you that we cannot really use directly the vibrational density of state because there are also other contributions, and we need this projection procedure. And now I want to show you why. So in this plot, what I have is the absolute deviation of the computed values from the experimental ones, from methane, ethane, and propane. Here, this gray shadow is the statistical certainty for my 2 picosecond trajectories. And this one is when I use my projection procedure. In this one is said if I don't project my vibrational density of state. And as you can see, the simple projection of the exactly two same trajectories reduce the statistical uncertainties from 10 kilojoule per mole to only 1. So you can see that it's really this projection and filtering procedure that make the things work. So I don't want to enter in detail this. I want only to say fastly, but we have also, for now, I show you data using trajectory of 20 picosecond. We have also a way that allows us to reduce the maximum length of a trajectory to 3 picoseconds. And this 20 and 3 picoseconds, I remember that you have to compare to the standard 50 to 1 nanosecond trajectories that usually are required. And with these 3 picosecond trajectories, you can see that this brown line here and here, we can still have a good prediction of the absorption free energies for these 3 cases. So with this, I would like to conclude. So I hope that I convince you that we have this simple strategy to improve the accuracy, not only of the enthalpic term, but also on the entropic term of free energies, and with a reduced computational cost, because 20 picosecond trajectories are something that now we can do in a couple of days, 1 week if your system is big. And I have shown you the case of the absorption, but this method can work for all the steps of your reactions. In particular, we want to test it now also in combination with other constrained molecular dynamics techniques, because it's fully compatible with them. And I want also to underline that since we are calculating the free energies by using the vibration density of state, the intensity is computed by the Fourier transform of the time correlation function of atomic velocities. We have also a way to assess spatial resolved entropy and enthalpic terms. And since we have a so fast convergence, we can also build these maps that usually are built only for classical molecular dynamics simulation, because usually you need so a long time scale to make them converge that a DFT-MD simulation is out. And this is for what we are pointing for the technical point of view, the research. But we want also, for now, we have tested it for the Shabazite that I've shown you, but we want also to extend the study, for example, for the reaction of methanols with alkane in the HM5, or to also reaction in methanol organic framework. And before I let you go, let me thank the people involved in this research. First of all, I want to thank Professor Sauer to propose me this really changing research 1 year and a half. And it was really been a pleasure to work in his group. And overall, I want to thank you for all the discussion, the support, the advice. And I want also to thank the Alexander von Humboldt Foundation for allowing me to do this research. And I want to thank all the group, the quantum chemistry group in Berlin, because it was really nice years there. And at the end, I would like also to thank my new group here in Nijmegen that has helped me a lot in this strange pandemic time to move and try to not me feel, even with the social distancing, they do a lot not to make me feel isolated. And I want to thank you all for the attention. Thank you.
Applause, applause. Please imagine that there is loud applause coming. So this was very exciting. Thank you very much, Daria Galimberti, for this exciting talk. Yeah, and we have seen you know Berlin, of course, so we can hopefully expect that you will come back one day actually to work with us. So thank you very much. Also for you, of course, the virtual certificate, which we send via email, and also for you, of course, we have another, it's not the same, for sure. The bucket of flowers, please go to Nijmegen. Ah, there it is. Perfect. Thank you very much. Great. So I would like to thank actually both of you very much to join us today and give this exciting talk. Of course, also to the to Holger Dauer and Franziska has to give the laudations. A special thank, I should not forget this, is going to Claudia Nasrallah, who have organized our awardee ceremony today. Of course, we always say it would be so great to meet in person and have talks and now have a glass of wine together or whatever. But I think actually this is really the best we can do in the moment. So thanks, Claudia, for the organization and that this worked so fine. And I'm pretty sure we will meet again then in person as soon as possible here in Berlin or somewhere else. So thanks to all of you and take care and have a nice weekend.
Thank you all. Stay healthy.
Yeah, goodbye.
Bye-bye.
Bye.
Bye-bye.